Yes, welcome to our classroom. Here we are going to discuss about the magnetic field outside and inside a long cylindrical wire. Okay, suppose if you are taking any cylindrical wire which is in the infinite distance, we have some uniform cross sections, right? So here we are going to discuss. So this is the wire. Okay, so which is having uniform cross section as A. Okay, and then inside the wire we have the radius as R, and outside it is also we are taken as R. Okay, so inside the wire R, outside the wire we are taken as R, uniform cross section. Don't confuse yourself, right? So this is a diagram here I have. So this is the wire which has the radius small a, and the current is passing as I here. Yes, the current is uniform throughout this wire, right? And I am considering the first ampering loop, this one, right? Number 1, that is the first ampering loop, and which has a radius of R. And the second ampering loop, that's outside this wire, right? So this is inside, this is outside the wire. So I have chosen two different ampere loop, one is inside, one is outside. Now we are going to find out what is the magnetic field inside and as well as outside, right? Move on to the outside. So outside means this one, second ampering loop. So the length of the wire, what is the length of this wire? Yes, the circumference of the length, L is equal to 2 pi r, and the current enclosed by it is I, right? And by Ampere's circuit law, we can write B into L is equal to mu naught into I. So L we have 2 pi r. So B into 2 pi r is equal to mu naught I. Therefore mu is equal to mu naught, B is equal to mu naught I divided by 2 pi r. Therefore I can write B is inversely proportional to 1 by r, right? B is inversely proportional to 1 by r. As the distance increases, the magnetic field will decreases, right? Okay, where it is? Exactly here. As the distance increases, the field will decreases now. Now move on to the field inside. Field inside means ampere loop 1. So again the circumference of the circle is 2 pi r, but the current is not same. In that first ampere loop it has I, but it has less than I. Why? Because inside root, right? So definitely it's clearly it shows that this second ampere loop, inside the loop it will have less than I value. That's why I write I dash. That I dash equal to I into pi r square divided by pi a square. What is pi r square? Yes, this one, right? The first loop divided by pi a square is the second loop. That is the axial, right? So pi a square. Therefore, if you cancel that will give I dash is equal to I into r square divided by a square. So by Ampere's circuit law, we can write BL is equal to mu naught I dash. So Y dash we have found here. So B into 2 pi r is equal to mu naught I a square divided by, I r square divided by a square. So simplified, B is equal to mu naught I r divided by 2 pi r a square. Therefore we can write B is directly proportional to R when it is inside. That means from this point to up to this point, the magnetic field value increases up to the surface of this wire. The magnetic field will be increases. At the surface it is maximum. From the surface it's going outside, that time it will be decreases, start to decrease. That's why we have drawn this graph, B versus R. When initially inside the axial, B increases, R is also increases. That is this first ampere loop. And when it reaches the surface of this wire, so B will be maximum only at A. After that it fall down to 1 by R, right? That is outside. Outside it will be decreases with respect to the distance increases, right? I hope you understand well. Thank you. See you in the next video.